Hi, today we're going to study chapter 29, nuclear physics. Nuclear physics. So we're going to study the center part, the nuclear. Again, this is the introduction. You still need to study the lecture notes and try some problems. Okay, section one, we're going to study some very basic property of the nuclear or nuclei. Okay, so this experiment, we have a short introduction in chapter 28. Okay, so we call the Rutherford experiment. So he performed this experiment about 100 years ago. That's 1911. Okay, because he want study what is the inside of atom. We know we cannot see inside of atom, not even today. But 100 years ago, he tried to find out. So since you cannot see a single atom, so he used a target, this foil, a very thin foil. This made by gold. Okay, here's two block and has two holes, and this is the particle source, and he used all the particles. All the particle basically is the nuclear of the helium. Every particle has two protons and two neutrons, so it's positive charge. So now the particle, the alpha particle, pass the two holes, then strike the target. And he wants to see, Rutherford wants to see what happens. So he and his student spent 4 years, perform this experiment. Okay, so here's green one's the detector. So he find most particles just pass through the foil, go about this area. Okay, so if you have 1,000 particles, let's say 1,000 particles, more than 900, 950 just straight out to this area. Now the 50 of the 1,000 going to change the angle, go this way, go that way. Even our field come all the way back to this part or that part. Okay, so that's what he find. Of course, he also use mathematics, calculate it. Then he have this conclusion. He tell us 100 years ago, inside of atom, mostly is empty space. It's nothing there. So this make the nucleus look so big. So really, the real size, the nuclear inside atom, just like a blueberry inside of, say, football stadium. So this part here is 100,000 times smaller than the atom. So inside the atom, just empty space. The nucleus so small, 10,000, 100 times smaller than the atom. So we say inside the atom is mostly empty, nothing. Okay, and why? Because you see, remember every particle is positive. So most particles just pass through because it's empty. Only few because so close to the center. Remember here we have proton and neutron, positive charge, like the gold, this one, atom of gold has 79 positive charge. Okay, so now these particles close by, they're going to repel each other because both positive charge. That's why they changed the angle. Okay, so from all the data and the calculation, so if closer, going to change bigger angle, further change smaller angle, even further not going to change. From all the information and from all the calculation, so we have a conclusion. So scientists repeat the same experiment again for last 100 years. We always have the same answer. So that's why we believe this model. Even we cannot see inside, but we know inside mostly is empty space. Nuclear so small. Okay, now we have a few important concepts. The first called nucleons. Nucleon. Nucleon. And more than one we call nucleons. So what is nucleon? Nucleons are protons and neutron. Proton is nucleon, neutron is nucleon. Together we still call nucleon. For example, this is carbon. Carbon has 6 protons, 6 neutrons. So how many nucleons? 12. Together we call nucleons. Okay. So the reason we give the same name because the proton and the neutron has almost same mass, same weight. So when we study nuclear energy, the mass, the weight is most important. So that's one reason we give the same name for both. So we don't say atom of the carbon has 6 proton and 6 neutron. We can say carbon atom has 12 nucleons. Okay, so this symbol we call nuclide symbol. If you studied chemistry, you know this symbol looks a little different. Because chemistry usually they give the atomic number on the top, either left side or right side. But no, this one here, okay, the atomic number at the bottom. So the capital X is the name of the give you the chemical symbol or nuclide symbol. Okay, so if this O means oxygen, C means carbon, my last name He be helium. So this gives the name. Now you see the two numbers at the bottom on the left side. This small number Z, this letter Z, give you the number of the protons. We call atomic number. Now this number here we call the mass number. This number will give you number of the nucleons, proton plus neutron. Okay, so this give you the name, the chemical symbol. The bottom give you atomic number equals number of protons. The A we call the mass number, the top one, equals number of nucleons. Okay. So now here's two examples. Suppose we have this sample here, and you can find the name. So if you have a periodic table, so you go number 17. So Cl give you the chlorine. Let's see if I have a table here. So you can use the periodic table. You can print one. You prepare one when you solve the problem. Okay, so that's number 17. And the bottom here gave you the name. Let's see if we can make it a little bigger. Okay, chlorine. Give you the name. Okay, see, for chemistry, these are atomic number on the top, left. Nuclear physics at the bottom, on the left. Okay, so now let's go back to our class lecture. Okay, so if I will ask you find, okay, what is these elements of the nucleus? You go the periodic table, find the name. So if I ask you how many protons, well, 17. Neutrons, okay, the top one, 35, give you the nucleons, a proton plus neutron. So simple math, subtract these two numbers, give you the number of neutrons. Okay, so this one has 17 proton, 18 neutron, and 35 nucleons. Here's another example. This one is mercury, number 80, next to the gold. Okay, so now the name is mercury, and how many protons? 80, 80 positive charge. Neutrons, the top minus bottom give you 120, 120 neutrons, and together 200 nucleons. Okay. Another concept we call the isotopes. So what is an isotope? The isotope is the atoms that have the same number of protons, but a different number of neutrons. Okay, so we have several atoms that have the same protons, different neutrons. We call them isotopes. Isotopes. For example, hydrogen. So most hydrogen is like ordinary hydrogen. One proton, no neutron. Deuterium is isotope of hydrogen. One proton, one neutron. Tritium has one proton, two neutrons. So they have the same number of protons, one, different number of neutrons. So we call them isotopes. And also the carbon. Carbon, we have a carbon 12, 6 proton, 6 neutron. We have carbon 13, 6 proton, 7 neutron. Okay, and the carbon 14, that's very popular, carbon 14 for dating. Okay, so 6 proton, 8 neutron, carbon. So we call them isotopes. Different neutron, but the same proton. So that's important. And then this we mentioned again before. When we study nuclear energy, of course, that's huge amount of energy. But we start with energy from one single nucleons or few nucleons, proton and neutron, just few of them. So we need a smaller unit. So we have atomic energy unit called electron volt. 1 eV. This very small unit equals 1.6 10 to the power negative 19 joule. So we need going to change the unit back and forth. Okay, 1 electron volt we call atomic energy unit. Energy unit equals 1.6 10 to the power negative 19. And we also have mega eV. That's 1 million electron volt. Equal 1.6 times 10 to the power negative 13 joule. Okay, so this is 1 U. 1 U, that's a mass unit, atomic mass unit, equals 1.6605 times 10 to the power negative 27 kilogram. Okay, this almost equals mass of 1 proton or 1 neutron. Very close to this number, not exactly. So 1 U atomic mass unit equals mass, roughly a mass of proton or neutron. Okay, more. So we studied the rest energy when we study chapter 26, special relativity. So mass can be converted to energy. Even at rest, the object carry energy equals mass times speed squared. So now, if I have 1 U, 1 unit, this little mass, how much energy, how much rest energy, so we can calculate. So now instead of 1 U, we use kilogram again, 1.6605 10 to the power negative 27, then times speed of light and a square. Okay, so give us this much energy. 1.49, we can just read the first few digits. 1.49 times 10 to the power negative 10 joule. Okay, so this is energy from just one atomic mass unit. 1 proton and 1 neutron will give you this much energy. Okay, so if you convert joule to mega eV, this is important. 1 U, 1 atomic mass unit give you this much energy, 931.5 mega eV. That's a lot of energy. So now we have a different unit. We need to convert back and forth. So when U times speed of light square will give you this much energy. We find from there. Or if we just divide by c squared both sides without any calculation, just divide by c squared, divide by c squared, we can see when U equals 931.5 mega eV per c squared. So now this becomes a mass unit, Okay, see, it's a little, you need to pay attention because we have a different unit now. So we have proton, neutron, and electron inside the atom. Okay, they have a positive charge, negative charge. Proton has positive charge, electron negative charge, neutron no charge, equals 0. Okay, so the mass of the proton and the neutron almost same. Neutron, if you check these digits, okay, a little bit heavier. So that's why neutron can decay. Decay change to proton. That's called the beta decay. So now, if we convert to other unit, the mass of proton and mass of neutron going to be equals these two numbers. Say 1.007276. It's the reason we keep so many digits. Okay, then the neutron a little heavier, and also we can use that unit. Electron 1,000 times lighter, very light. So the mass of atom almost equals the mass of the nuclear, because electron so light, and also because inside the atom is mostly empty space. Okay, so that's mass of electron, and convert to U and this unit. So we have more talk about the nuclears because we cannot see directly. Let's take this one. This one should be this carbon. To be okay. 1, 2, 3, 4, 5, 6. 6 proton. 6 proton, and 6 neutron. Okay. 1, 2, 3, 4, 5, 6. So this is the carbon. So we take this as the example. So nuclear force is very different from other forces, different from force of gravity, electrical force, and magnetic force. Because other force has a long range. Okay, for example, like gravity, the Earth and the Moon, Earth and the Sun attract each other all the time over a far long distance. They still can interact each other. Electricity also, we can receive signal from Little Rock, from California, and even from a satellite, because the electric force, electric signal can go long distance. Well, not nuclear. Nuclear has a very short range. Okay, only work if the proton neutron close enough. Or simply speaking, nuclear force only work at size of nuclear. Okay, so now we can understand why so many protons. We have 6 of them, but we have bigger nuclear like Mercury, have 80. So many positive charge can stay together. Why? Because nuclear force is so strong. Because the strong nuclear force, we also have a weak nuclear force, that's radioactive decay. So strong nuclear force is like a few hundred times stronger than the electromagnetic force. So nuclear force is stronger than other forces, but only at small space. So proton and proton, they repel each other, but why they can stay together? Because nuclear force so strong, only at a small space. Okay, but even so, nuclear force has limit. If you have too many protons and neutrons, if nuclear is so big, then nuclear force cannot hold them anymore. So assume you have like few hundred. So this one and that one is too far. They cannot hold each other by nuclear force. Then electrical force is going to repel each other. So that's one of the reasons for radioactive decay. Okay, and also the reason we have neutrons. Why have a neutron? Because neutron has no electric charge. So neutrons stay between the protons, can make the nuclear more stable. Otherwise, they're too close, they're going to repel each other. But between proton and the neutron, we still have a nuclear force, which is very strong. So that's why we have neutron stick with proton because nuclear force. And this diagram just tell you when the nuclear become bigger and bigger, and they have more and more neutrons. So the bigger, the heavier nucleus, always more neutron than proton. That's necessary. And also we can understand after the lead is pretty stable. Okay, after lead, every elements become unstable because they have too many nucleons, too many protons. So let's say this periodic table again. So lead, okay, this lead is the last stable one, 82 protons. After this one, 83, 84, they're unstable because too many proton neutrons. Then all these are man-made elements. You cannot find them. The heaviest one we can find on Earth is uranium, 92 protons. After that, see, 93, 94, all the way, they are man-made elements. You cannot find them because they are unstable. Okay, so we go back. Okay, so now we come to the most important part. We're going to discuss section 2, binding energy. Binding energy. So binding energy really is the nuclear energy. Nuclear fission, nuclear fusion, because binding energy. Okay, so now around 1930, well, we talk about 90 years ago now. Okay, scientists find this. Scientists find the nucleus has smaller mass than its separate nucleons. When proton and neutron combine and form a nuclear, certain mass is missing. Okay, mass is missing means what? Means certain energy is given off. Then this is bonding energy. Because energy are mass related. Mass times speed of light square give you energy. Okay, let me read again. When the nuclear has smaller mass than its separate nucleon, we mean this. Okay, so here we still take the carbon as the example. So totally we have 6 proton, 6 neutron. And you can measure the weight. We can do that. Okay, so you find a mass of this nuclear. Now, if somehow you can take part of them, so you find 6 proton plus 6 neutron are heavier than the nuclear of the carbon. So when proton and the neutron combine, make a nuclear, it becomes lighter. When they're separate, they're heavier. combine later. So we say certain mass is missing. Certain mass is missing, we call missing mass. And where's the mass go? Well, it changes to energy. And that energy we call bonding energy. So again, when proton neutron combine, form a nuclear, become lighter, certain mass is missing. Then the mass change to energy. We call binding energy. Now, the bonding energy will have three definitions that are all important. First is energy equivalent of the missing mass equals the mass missing times speed of light square. That's bonding energy. Second definition, the binding energy is energy needed to complete break up nuclear to proton and neutron. So if they are combined, you want to break up, you need to give energy in, right? You need energy to break up. How much energy? It's the same energy we call bonding energy. And also the energy given off, released when proton neutron combine to make nuclear. So let's just take a little time. So we say we have 6 proton, 6 neutrons. When they combine together, they're going to give you energy, give off energy. But now you say, okay, we want to break up this nuclear. You break them up, become individual. Well, you need to give in energy. The energy out and energy in is the same energy. We call them bonding energy. Okay, so now if we calculate, we can find how we can escape the detail. So here's the example. So now if you measure mass of hydrogen plus 1 more neutron, hydrogen has no neutron, just 1 proton. So hydrogen atom plus 1 neutron going to be this much. So now the mass of deuterium, this one has 1 proton, 1 neutron, already combined, is this much. See, when they are separate, heavier. When they combined, lighter. That's 1 proton and 1 neutron. What's the difference? Let's subtract these two. Give you a little bitty mass. That's the missing mass. We use a delta M equal 0.0024 U. But this little bitty mass convert to energy. This mass times speed of light square will give you this much energy, 2.2 mega eV. That's quite a bit of energy. 1 proton and 1 neutron combined, just 1 proton, 1 neutron will give you this much energy. Okay, so scientists think, oh, if we can find many protons, many neutrons, and just let them combine, what's going to happen? A lot of energy released, right? We can use a huge amount of the bonding energy. Well, that is true theoretically. But we cannot make it happen because we cannot find many proton neutrons. What we can find? We can find the different elements. Again, look this one. We can find the hydrogen. We can find helium. Every element until the heaviest one, uranium. This last one. That time, 1930s, we don't have other elements yet. So we can find this many different elements. So that means proton, neutron already combine, make elements. We don't have many free proton neutrons. Okay, so now what do we do? Well, scientists think, well, so we don't have proton neutrons. How about we break up the atoms? So if we break up mercury, for example, the mercury will give you what? 200 proton neutrons, right? Then we have proton neutron. That's correct. But when you break up, so energy just like how much they combined. So you don't get any energy. So for example, we still take the carbon. Okay, so when 6 proton, 6 neutron combine give you bonding energy. But if you want to break up this nuclear, you're going to use same amount of energy. So you don't get any energy free. Well, what we can do? Because that's a lot of energy. 1 proton, 1 neutron give you this much energy. If you calculate 1 kilogram, just 1 kilogram, 2 pounds, 2 pounds of uranium will give you a lot of energy. How much? The whole state of Arkansas can use for 1 month. So we don't do the calculation here now. Okay, so now what we can do? Scientists find, okay, let's check. Okay, the elements one by one. See which one can give you more energy. We can break up some elements and make some other elements as long as we have more energy out than energy in. So now first thing we have to say which one give you more energy. Okay, so now they check energy, the bonding energy. So when proton, neutron combine, make helium, make aluminum, make the gold, silver, and lead, uranium. Okay, so from hydrogen all the way to uranium. See which one gave you more energy. Well, but you cannot just check compare the energy because they have a different number of proton neutrons. So it's better if you check the bonding energy per nucleons. So that is total energy divided by number of nucleons. So give you average. So we want to say in average, which element give you more energy? Okay, so simply speaking, they find this curve. Some people say this is the most important diagram in history of science. And this diagram gives you key of the nuclear energy. So scientists find, okay, not a very light one, like hydrogen or helium. Not a very heavy one, like radon or uranium. Okay, so the medium-sized one, this part here, the center at iron, give you more energy. So the medium-sized one give you more energy. Medium-sized one give you more energy. Okay, so this give you clue. Okay, so we can either break up heavy one, like uranium, then make a medium-sized one. Why? Because you're going to have more energy output. So that's called nuclear fission. You break up heavy one, make the medium size. Or if we can combine smaller one, okay, combine smaller one, make a medium size, you're going to have more energy output because medium size give you more energy. So this is called nuclear fusion. Either way, you want to make a medium size. Okay, so now let's see. Here's a calculation. Usually I give this to classroom. Okay, see how we can do this. So we calculate. So take a small 3 examples. This is the light one. This helium. This heaviest one, uranium, and this medium sized one, iron. Okay, so let's see which one give you more energy. So we only go over the helium. Okay, so we can easily find this number. So mass of nuclear of helium is this much. Okay, then helium has 2 protons, 2 neutrons. So now when okay, so Z, that's the atomic number time mass of the proton, plus this A minus Z give the number of the neutron time mass of neutron, and mass of proton and neutrons given. So if we do this, basically it's 2 times the mass of proton plus 2 times mass of neutron will give you this much. Okay, you see when they combine, it's a little lighter, 4.002. When they're separate, 4 individual proton neutrons, 4.03. It's heavier. And here's the difference. We call the missing mass. Then we convert to the energy. This is bonding energy. Times speed of light square give you this much energy. That's a total energy. So now this is the bonding energy of helium. Now how many nucleons we have? 4. So you divide by 4. Divide by 4 give you average 6.8 mega eV. So helium give you 6.8 mega eV per nucleon. So if you do the same thing for the medium size iron, you find give you more energy, 8.55 mega eV. And uranium, you can do the same thing. You can find 7.37. All these numbers are very easy to find out. Okay, so which one give you more energy? The medium size give you more energy. The medium size give you more energy. Okay, so that's conclusion. So most important for us, this part is the concept. So conclusion is when nucleons combine to form a medium-sized nuclear, a medium-sized one, what happens? More binding energy gives off. So now you have 2 ways to make nuclear energy. One we call nuclear fission. You can split or break heavy one like uranium. Okay, heavy one make 2 medium size, then more energy out. So you're going to have output energy. So we call nuclear fission. Second one we call nuclear fusion, which is joining 2 light nuclei to form a medium-sized one. Okay, smaller one combine make a medium-sized one. Then what happens? More bonding energy give off. So that's the 2 of them. One we call nuclear fission, one called nuclear fusion. So the detail we're going to discuss in chapter 30. So we're going to stop right here, and we're going to have a second part for chapter 29.